Welcome to CEDA-Labz. In this module we will study state machines and its designing in Verilog. Combinational logic units are a type of logic circuit whose output is a pure function of the present input only. Finite state machines, used in sequential logic, have outputs that depend on both the present input as well as the history of the input. State machine is a machine consisting of a set of states, a start state, an input, and a transition function that maps input and current states to a next state. Machine begins in the start state with an input. It changes to new states depending on the transition function. The transition function depends on current states and inputs. The output of the machine depends on input or current state. It is called a finite state machine because it can have, at most, a finite number of states. It is composed of a combinational logic unit and flip-flops placed in such a way as to maintain state information. It is of two types, Moore machine, Mealy machine. We will be discussing them in detail later. Examples of state machine are vending machines, which dispense products when the proper combination of coins is deposited, elevators which drop riders off at upper floors before going down, traffic lights which change sequence when cars are waiting, and combination locks which require the input of combination numbers in the proper order. A FSM can be represented in two forms: state transition table, state diagram. First we will talk about state transition table. The state transition table has the following columns. Current state contains current state code. Input values of the FSM. Next state contains the next state code. Output, expected output values. Another form is state diagram. The following image shows the state diagram of FSM. In this representation every state is a node. A node is represented using a circular shape and the state code is written within the circular shape. The state transitions are represented by an edge with arrowhead. The tail of the edge shows current state and arrow points to next state, depending on the input and current state. The state transition condition is written on the edge. The initial or start state is sometimes represented by a double-lined circular shape or a different color shade. The codes 0, 0 and 0, 1 are the state codes. Now let's talk about Moore machine. In Moore machine the output depends only on current state. The advantage of the Moore model is a simplification of the behavior. Simplification is because of dependency on only one variable. Here is the state diagram. A is the input. Inside every circle the text is state code by output. Here, there is only one output. In state 1, the output is 1. And whatever may be the input, A, state moves towards state 0, 0. Similarly, for state 0, 0, output is 0 whatever may be the input. But, when the input is 0, state transition is towards itself, and when input is 1, transition is towards state 0, 1. In similar manner, for state 0, 1, output is 0, and when input is 0, state transitions towards state 0, 0 otherwise to state 1, 1. This figure shows the block diagram of a Moore FSM. The output function doesn't depend on input. The current state function updates the current state register. Current state register or memory element is the compulsory element of any state machine because it contains states. Even next state logic block and current state register block together can be said to be a state machine. Only after addition of output logic block it turns into a Mealy or Moore machine. Here next state logic and output logic are combinational circuitry and current state register is sequential circuitry because it stores the states. In Mealy machine the output depend on both current state and input. The advantage of the Mealy model is that it may lead to reduction of the number of states. Here is the state diagram. This is an example of a Mealy FSM. The text on the arrow lines show input / output. A is the input and X is the output. Refer the diagram. At state 0, 0, when input A is 0 and output X is also 0, state transitions to self. And it transitions to 0, 1, when input is 1 and output is 0. Similarly, for second state, 0, 1, it transitions to 1, 1, when input A and output X, both are 1, but transits to 0, 0, when both are 0. For state 1, 1, whatever be the input, output will be 1, and it will transit to state 0, 0. The block diagram of the Mealy FSM is shown here. The output function depends on input also. The current state function updates the current state register. Number of bits depends on state encoding used. Now let us start with some examples in order to understand Verilog coding for state machines. First of all, let us go through some facts related to state machine designing. States are not ports in state machine, they are internal circuitry. State machine have two inputs, one input, one clock, and one output. Although, clock is for transitions. If reset is also present, then its initial state will be considered according to reset. We prefer active low reset mostly, and that, two-way synchronous for state machines. State machine is coded in behavioral modeling only. It is not possible in any other modeling. So here is the state diagram of a state machine. We will be writing Verilog code for this machine. Just by having a look at this state diagram, can you tell which type of state machine it is? It is a Mealy machine. As we can see, transition is dependent of input and output. Reset is also present, so its initial state will be A. We can do a state machine designing in 3 styles. Here is the first one. We start with same procedure, keyword module and module name with port list. Then ports are declared. Here we declare 2 registers of 3-bit PS and NS, representing present state and next state respectively. As we know, parameters are used to define constants, so we define the 3 states with parameter A, B and C. In this style, we will design different always block for every block of state machine, that is, one always for current state register or memory element, second always block for next state decoding logic, and another always block for output logic. As the memory element is the sequential block, event will occur only when there is transition of clock or reset. So, sensitivity list will consist of 2 events: passage of clock and nudge of reset, active low asynchronous reset. This always block indicates that if reset is low, then present state will be A, otherwise it will be the next state. Here is the design of next state logic block. Obviously, next state will depend on input A and present state. Using case statement, we are designing this block. When present state is A, first case, then as we can see from the diagram, when A is 1, next state is B, otherwise it is A itself. In second case, if present state is B, then according to the state diagram, when A is 1, next state is itself B, otherwise it is C. Similarly, in case of state C, when A is 1, next state is A, otherwise it is B. Now we will design output logic block. Again, output will depend on input and present state. As we designed next state logic, in similar manner we will design this block also. In our first case, as we can see from the state diagram, when A is 1, Y is 1, and when it is 0 it is still 1. In second case, B, when A is either 1 or 0, Y is always 1. And in last case, C, when A is 1, Y is 0, and when it is 0, Y is 1. This is the best style of designing state machine because there is a separate always block for all blocks of state machine, resulting in less error and less confusion. Here is the test bench for this state machine. We may design the design block in any style, but test bench will remain the same. Here we are initializing and generating clock pulse, and also providing input continuously as we used to do. In coding style 2, we are combining the coding of 2 combinational blocks. That is, we are having a separate always block for sequential circuit, that is memory element, and separate always block for combinational circuitry, that is next state decoding block and output logic block. Unlike in first style, we were having separate always block for each state machine blocks. memory element coding will remain the same. In combined always block, we will combine the next state result and output in the same if-else block as we can see. Each if-else block of every case will contain the information, which is the next state and what will be the output. In third coding style, we have only one always block. Coding of each block that is next state, output logic and memory element is combined, in one always block only. This coding style is wrong but will give correct simulation result. It is wrong because clock will be divided between the three blocks of state machine, which is necessary for sequential one only. It is a state diagram of a Moore machine. As we can see, transition only depends on the current state. Now we will design this state machine using Verilog. In a similar manner, we are designing the Moore machine with the same syntax and procedure. Starting exactly in same way, module and module name followed by port list. Then ports are declared, and two registers of 2-bit, representing present state and next state respectively is declared. Four states, A, B, C, and D, are defined using parameter keyword. We will design it in the first style of coding as it is the best style for modeling the state machine. And, in this style, three different always block are designed for every block of state machine, that is, different always block for memory element, next state decoding logic, and output logic, as we did when we designed Mealy machine. First one is for memory block, which is sequential in nature, so event will only occur when there is transition of clock or reset. This always block indicates that if reset is low then present state will be D, otherwise it will be the next state. While designing the Mealy machine, we learned how to design next state logic. In the same manner we will design this next state logic code. Next state will depend on input, A, and present state. Using conditional statements, we are designing this block. First case, present state is A, then as we see from the diagram, when input A is 1, next state is B, otherwise it is C. In second case, state B, then according to the state diagram, when A is 1, next state is C, otherwise when input is 0, next state is itself B. Further, C and D case of the next state logic. For case C, when input A is 1, next state is A, and when input is 0, next state is D. In last case D, when input is 1, next state will be C, otherwise it will transit to A. The difference only comes in the coding of output logic. As the output only depends on the current state and not on the input, if-else block is not needed. In a FSM design, each state is represented by a binary code, which is used to identify the state of the machine. These codes are the possible values of the state register. The process of assigning the binary codes to each state is known as state encoding. The choice of encoding plays a key role in the FSM design. It influences the complexity, size, power consumption, speed of the design. If the encoding is such that the transitions of flip-flops of state register are minimized, then the power will be saved. The timing of the machine is often affected by the choice of encoding. The choice of encoding depends on the type of technology used, like ASIC, FPGA, CPLD, etc., and also the design specifications. The following are the most common state encoding techniques used: binary encoding, one-hot encoding, gray encoding, Johnson encoding, one-cold encoding. In the following explanation, assume that there is n number of states in the FSM. The code of a state is simply a binary number. It is good for arithmetic operations, but it may have more transitions, which may lead to more power consumptions. Also, it is prone to error during the state transitions. The number of bits is equal to log 2 n rounded to next natural number. Suppose n equals 6, then the number of bits are 3, and the state codes are S0, 000, S1, 001, S2, 010, S3, 011, S4, 1, 0, 0, S5, 1, 0, 1. In one-hot encoding, only one bit of the state vector is asserted for any given state. It is another low-power coding style, requires more no-of bits. It is useful for describing bus protocols. All other state bits are 0. Thus if there are n states, then n state flip-flops are required. As only one bit remains logic high and rest are logic low, it is called as one-hot encoding. If n equals 5, then the number of bits, flip-flops, required are 5, and the state codes are S0, 0, 0, 0, 0, 1, S1, 0, 0, 0, 1, 0, S2, 0, 0, 1, 0, 0, S3, 0, 1, 0, 0, 0, S4, 1, 0, 0, 0, 0. Gray encoding uses the gray codes, also known as reflected binary codes, to represent states where two successive codes differ in only one digit. This helps as reducing the number of transition of the flip-flops outputs. Good as they reduce the transitions, and hence consume less dynamic power. Also, they can be handy in detecting state transition errors. The number of bits is equal to log 2, n, rounded to next natural number. If n equals 4, then 2 flip-flops are required and the state codes are S0, 0, 0, S1, 0, 1, S2, 1, 1, S3, 1, 0. In Johnson coding also there is one bit change, and can be useful in detecting errors during transitions. Here, more bits are required. It increases linearly with the number of states. There are unused states, so we require either explicit asynchronous reset, or recovery from illegal states, even more hardware. It is just opposite of the one-hot encoding style. Here only one bit is 0, rest bits are asserted for any given state. Now, let's move into the flashback. In this tutorial we learned what finite state machines, its kind, Mealy and Moore machine. We did some designing example of both type of state machine. We also studied about state encoding techniques and its types. Here is a state machine state diagram for you. I hope you will be able to design it.